Good morning, students. Uh, Welcome to the CD's class. Last class, we discussed about semantic analysis. So, yesterday we completed that particular topic. So, excluding semantic analysis, in the module 5, we have intermediate code generation. Here also, we're going to get a few varieties of problems. And then the next topic I anticipated was we have code optimization, but according to the syllabus, code optimization is not there. You people do have only code generation. Okay. As of now, how much ever is there in the syllabus, we'll cover the same thing. Fine. After that, as a live recording, I'm going to do the shift reduce parsing or bottom-up parsing, and I'm going to place the video. So that way we are going to do it. As of now, if we can consider three more classes, 2 or 3 more classes, we can complete this, what you call module 5. And another 2-3 classes, we can complete the, what you call left out portion in module 3. So in that sense, we would have completed the complete compiler design portions. Fine. So today's discussion is intermediate code generation. In this also, we have few varieties of the problem that anyway I'm going to solve it and I'll let you know. But the conceptual thing, we shall cover it today. Fine. And fine. We shall do that like that way. So what is the objective is intermediate code generation, representation, and intermediate languages, their classifications. And 3 address code is one of the widely used what you call intermediate representation and how to represent different programming language constructs using this 3 address code. For example, the declaration, assignments, arrays, pointers, everything. And in this, in going further, the Boolean expression, logical expression, how to represent all those things. So the problems regarding that, we shall do it on the board. Fine. But try to understand the concepts today. We shall do the problems once after this. Fine. Probably tomorrow's class, we'll do that. Okay. What is it? Why it is needed, how it is done. These 3 aspects we should understand. What is it? First and foremost, try to understand why intermediate representation is needed. When we write the program, we'll write the program using the syntax and semantics of the programming language. Whichever the programming language it is, we use the syntax and semantics of that. But we checked the syntax by using syntax analyzer and ensure that our programming constructs are syntactically correct. Later, we gave it to the semantic analyzer. There we ensured that the syntactically correct structure is semantically correct. And before all these things, we did the tokenization, that is lexical analysis. Right. So these 3 phases are just analysis phase, so as to validate our code is lexically correct, syntactically correct, and semantically correct. So these 3 phases worked on the what we call the source program. No conversion has happened till now. So means to say they need the programming language details. But the next set of phases, that is code optimization and code generation, don't need what we call it as the programming language details, nor they need the machine language details. Means to say the instruction set addressing more of the thing is not needed. So as to optimize the code, we should bring our source code into some sort of representation which is free from programming language details and also which is not equivalent to the machine language instructions. That's what we are supposed to do. That's the reason we are going for code intermediate representation of the source code. So this is the first translation of your source code, which will be converted into some sort of intermediate representation. I'm telling you, there are different intermediate representations. We shall see all those things. Fine? Yeah. What is IR? An abstract machine language that can express the target machine operations without much of programming language details nor of machine language details. As a compile time data structure will be used. We use different data structure to represent IR code also. encodes the compiler knowledge of the program, and also this is what is the specification. So front end means at the source code level, we use different programming language which is converted into intermediate representation. Later on, after the code optimization, they will be converted into the target code depending on the machine architecture. Here we have you Spark, MIPS, NTM. You know, every target machine will have its own addressing mode, instruction set, memory representation, etc. Just like in SIC and SIC-XC we have seen. Fine. Okay. Where it is used, this is what is the flow. The front end, that is all our analyzers, gave us the IR code. Means after semantic analysis, intermediate representation is done. And what is this middle end then? The middle end is nothing but your code optimizer. It takes the IR code, which will not convert it into any other representation, but in turn gives you an optimized IR code, which is much efficient than the bare or the raw IR code. And that is given to the backend, which is your code generator, which is going to convert it into the target. But if at all we look at the Java programming language, we stop just immediately after middle end. That is just after the optimization, we obtain the intermediate representation, and that is later given to your JVM so as to do the task of the backend and produce the target. Fine, that's how it works. So this is what we have discussed. Fine. How it is used? Yeah, the first statement is most important. There is no standard intermediate representation. It is decided by the designer of the compiler. Which IR representation should be used is decided by the designer of the compiler, right? So there are so many. And as a translation takes place, IR is repeatedly analyzed and transformed. Compiler users want the analysis and translation to be fast and correct. This is what is the property. We don't want the IR generator or the code optimizer consumes a lot of time and yield a very less result. That's not what we expect. Compiler writers want the optimization to be simple and easy to understand and easy to extend. Okay. Yeah. And so that's the reason IR should be simple and lightweight. Okay. IR, why it is used? Yeah. Is a good software engineering. These and all are just the properties. You can just look into it. Good software engineering technique, break the compiler into modules or manageable pieces, isolates the backend from the front end. Yeah. Enable machine independent optimization. If we are not doing the optimization, absolutely IR representation itself is not at all required. The main reason why we go for IR representation majorly is for optimization. Okay. Yeah. How it is created? Yeah. See the wordings? It is a wizardry rather than a science. We need to express the computation as it is by removing the unwanted programming language details. That's what is the objective, or that's what is the target to be achieved. Yeah. So each compiler uses 2 to 3 IR representations, and majority of them we use what we call the 3 address code. But we shall see the hierarchy. We have 3 levels of IR codes. One is high level IR, preserves the loop structures, arrays, everything as it is in the programming language, and just can convert the expressions, whatever is there, the programming language. Middle level IR reacts a range of features, reflects range of features, which is set of source language things will be used. Language independent, good for code generation. And last level is low level IR, similar to our mnemonics and operands or assembly language code, which is also not suitable. So high level IR is also of not much use, and low level IR is also of not much use. So we should opt for a middle level IR. That's the reason we usually go for 3 address code. Okay, these are some of the expected properties of your intermediate code generator. It should be easy to generate, easy for manipulation, cost of manipulation, level of abstraction, freedom of expression. Means to say freedom of expression, we should discuss on this. We have a lot of programming language constructs, isn't it? So we have conditions, we have loops, we have different types of operators, arithmetic, relational, logical, all these operations, and we have declarative statements, and we have assignment statement, we have pointers, we have structures, all these things. Here, IR should be capable of representing everything. Why? For example, yesterday I told you about the abstract syntax tree and directed acyclic graph. The abstract syntax tree and directed acyclic graph is also an IR representation, but it can represent only the mathematical expression. But I cannot represent an array by using an abstract syntax tree, or I cannot represent a loop by using abstract syntax tree or diagram. That is not possible. So we need some sort of IR representation which can represent all programming language constructs in a same way. So that's the freedom of expression what we need. Okay. Size of the typical procedure, uh, the should not increase the code or should not reduce it. The major important thing is that we need to have the categories of IR. This is the most important thing what we need to see. Structural IRs, which we have already seen, the abstract syntax tree, directed acyclic graph. All these things comes into this category of structural IRs, which are represented graphically, right? Highly used in the source translations, have large number of nodes and edges, like abstract syntax tree and tag. This is as simple as that, which you have already seen. Linear IRs. This is the most important thing what we need to understand. The linear IRs are written in a sort of instructions. Linear IRs are not structural. They are not tree sort of things. They are written in the form of what you call instructions, right? Pseudocode or some abstract machine language. Large variation in level of abstraction. Simple, compact data structures can be used to represent them. So, which can be, we used what you call doubly linked list, and we used linked list with singly linked list for representing abstract syntax tree and tag. But here we can use just a multi-dimensional arrays for representing the linear IR. So it is going to be easy for us to place these things in the what you call data structures, and can be further used by our what you call further used by three address means sorry your code optimizers. Okay, so easy to rearrange during the code optimization, all these things. So one three address code is widely used, and one more variety is stack machine code, which is also a linear intermediate representation. Okay. Beyond this, we use a hybrid uh, intermediate representations, which is a combination of a structural and linear array. One of the variety of that we call it as control flow graph. But as you people don't have the code optimization, you'll never get a chance to learn about this. If time permits, I'll show you this, wherein we'll divide the linear IRs into basic blocks, and these blocks are arranged such a way how the control flows from one block to the other. So that gives us a sort of flowchart sort of representation while representing. Okay. One second. Okay. We shall see the stack machine code first, and then we're going to see the what you call three address code. Uh, yeah, stack machine code we shall see, and then we go for three address code representation. The stack mesh, see there we have an example x minus 2 into y. This is something to our what you call infix to postfix representation or expression evaluation. What you do is push x, then push 2, and then push also the y. Then we apply the multiplication between 2 and y, and then we perform subtraction between 2 into y and then x. So this will have, after the operations, the result of 2 into y, x minus 2 into y on the top of the stack, right? And how is it? It's a compact, mostly zero address of course, and easy to generate, simple to translate, and all those things. But this sort of representation suits well for our what you call mathematical expressions, but applying same for your loops, for example, your for loop or a while loop, is a tedious task, may not be a optimal solution. So for that reason, we go for the next sort of representation, that is our three address code representation. Our three address code, please have a look at this. It is a linear IR. I'm repeating, it's a linear IR, wherein we'll be having number of instructions, such that each instruction is of the form Y operation set. Means each instruction at the max, we can have one operation, right? What is an operation? Any mathematical operation is an operation, including the assignment, arithmetic operation, logical operation, or relational operation, or even the assignment is considered as an operation. And please, you should bother about the x. X is not a program variable, but it is a temporary compiler generated variable. That means a temp space. So assignment of the result of y operation z to x will not cost you an operation. Fine. So for that reason, so each instruction in your three address code will contain one and only one operation. That is the only logic of writing the three address code. So the three address code is capable of expressing every programming language construct. It may be a condition, it may be a loop, or it may be a relational operation, logical operations, everything. We shall see some problems also using this. Okay. For example, here x minus 2 into y, the same example which we have seen, and that value should be assigned to z. Now, t1 is equal to 2 into y. See that 2 into y is the only operation that is happening, and the result is stored in t1. Then x minus t1, that is the result 2 into y, is in the temporary location t1. X minus t1 is happening, and that is stored in t2. So what about z? That's not been shown here. So the next operation is supposed to be z is equal to t2. Means assignment to a program variable will also cost one operation, and that should be considered as a separate three address code. Fine. So I cannot do x minus t1 is equal, z is equal to x minus t1 cannot be done, because it is assignment to a program variable. That's a separate operation. Fine. Yeah, simple form of expression advantage compared from form direct naming, adds names to the intermediate values, can include forms of prefix, postfix, code, often easy to rearrange. But beyond all these things, the major advantage is all programming language constructs can be easily represented using the address code. We shall take each one as a separate example, and we will do it. So such sort of problems are even as something like convert the given code to the address code representation, and then representing them using different data structures like quadruples, triples, and indirect triples. So that need to be done. Fine. So we shall see all of them. Yeah. Typical statements allowed include. Yeah, just have a look, but I don't think so. We can grasp the complete picture of the address code representation through this. We'll do that separately. Fine. We have something like x is equal to y operations that yes, we can represent using what you call three address code, and a copy statement can be represented. Jump statements go to L, something like that, can be represented using three address code. Conditional jumps can also be represented using three address code, something like x relational operation, y go to L, right? Index assignments, that is your array element value assigned to a what you call variable can also be represented, and the other way around can also be represented. That is, array element is assigned with a variable value. That can be done. We should we should solve some problems regarding this. We shall do that. Fine. What and all can be represented using three address code? Pointers can be represented, and yeah, if you remember pointers, means if you look at pointers, the pointer is indirect addressing that's happening. Indirect addressing that's happening. Okay, that also need to be represented using three address code. Okay, procedural calls, call to a function can be represented using three address code. So therein, parameter computation should be done first, and then the function call should happen. So these are all the categories. So I think we have covered it, right? Can be represented using three address code. That's the reason three address code is the strongest form of intermediate representation. Yeah, I don't go with this slide and explain what is it, because it leads to a lot of confusion. But I'll do it using a problem and can see that. Okay. Okay. One second. This and all is not needed. Yeah, we straight away come here. Fine. Three address code is a linear IR. We write the instructions such that each instruction contains one operation. And there are some standard data structures that are used to represent the three address code. One such data structure is called as quad numbers. Quad means 4, means it will have 4 columns. It will have 4 columns. First is operator, second is argument 1, third is argument 2, and the final one is result. So means to say it is capable of representing our three address code easily. Why? The reason is every instruction in your three address code contains an operation, maximum of 2 operands, correct? X plus Y, right? So 2 operands, argument 1, argument 2. And the result, sorry, plus is the operation, X, Y is the 2 operands, is equal to T1. That is where the result is. So we can represent them easily. Okay, just have a look at the order. Here they have taken a instruction at the assembly language level for representing it. So we have used load R1 comma Y. So argument is Y, argument 1 is Y, argument 2 is no argument, and the result is in the 1, means that is T1. We can next load L with R2 comma 2. 2 is the argument 1 and the result in 2. You can write T1, T1, T2, T3 like this. But anyway, I'll go to solve it and I'll show it to you. We can do it. So quadruple is a 4 tuple system, or 4 columns will be there, and we're going to represent. But anyway, 4 is of too much. So we can go for a triples. Instead of 4, it will contain 3 columns. Operation, argument 1, argument 2. And the argument, each of the row in our triples are given a relative numbering. Something like in arrays we use indexing 0, 1, 2, 3 like this way. So the same will be given, and that is going to indicate the result of that particular operation. Anyway, we shall take an example and solve it. No issues. Fine. So like this way. Here 1 in parenthesis, 2 in parenthesis, 3 in parenthesis. This represents the triples. Right. And an indirect triples is a triple, but these addresses will be stored in an array of pointers which will going to point to that. There is a specific use of this indirect triple, because if suppose I have a big program of 100 lines or 200 lines, I have one function which is having sometimes 10 lines. Then that is converted into 3 address code. And if it is represented using triples, I should point to the specific function or the code the address code of specific function or specific loop. Then I need to go traversing from the beginning. Instead, we can have an array of pointer which can point to the beginning of that particular code, whatever the section we need. That way, the indirect triples will going to help us to locate the code easily and make the three address code representation modular or block by block can be done by using indirect replace. So these are the three types of representation. So then hybrid, that is control flow graph, it looks something like this. Each of them is a block. A block is a section of code where the control enters at the beginning, leaves at the end. For example, if it is a loop and the loop is true, then we enter into the loop and we only leave the loop at the end of the statement. And if suppose we have some unconditional break or continue or something like that, then we'll going to terminate from it. So each of the block is containing set of the address codes and their control flow is represented. Fine. This is what we call it as hybrid IR control flow graph, but anyway, not there for you people. So that's what is it. Which one to use? The choice is of the designer of the what you call compiler. Which one ever you want to choose, you can. AST or the other structural representation can be used at the stage of syntax analysis or semantic analysis, or usually we use flattened to linear IR. So initially we'll build the abstraction syntax tree or directed acyclic graph later on. So as to represent all other programming constructs, we'll use uh, linear IRs. Okay, and the hybrid forms are used during the optimization. As I told, we construct the basic blocks and control flow graphs so as to identify the control flow and optimize the blocks, and optimization can also possible to be interacts, right? So this is the end of the chapter, but we haven't solved the problems that we'll take care in the next class. But as of now, conceptually, this is the end of the second topic that was there in your what you call module 5. We are only left out with code generation. Right? Thank you. We shall stop here. So continue in the next class.